Hey boys and girls, welcome to the lecture number 34 of this course, which is called chemistry. The code for this particular course is CH101 for odd semester and CH201 for the even semester. This is G Chakraborty from the Department of Chemistry, and you people are watching this particular lecture, which is based on the topic spectroscopy, right? Now this is lecture number 34. We have successfully completed 33 lectures, and from the last lecture only we people have just went into the last and final module of chemistry, that is the module 5, okay? And the topic is spectroscopic analysis, right? And in the last lecture we have seen the details about UV visible spectra. We have seen that how UV visible spectra can be used to detect different functional groups present, what is absorbance, what are the different type of shifts that can be observed, what is HOMO, what is LUMO, and how the absorption and emission spectra takes place. All this we have seen, okay? This was the matter of the last lecture that people have seen, and in this lecture we are having IR spectroscopy or the infrared spectroscopy, right? So in this lecture we are going to see the details of these spectroscopies, which is called IR spectroscopy, right? So let us start the lecture. So as you can see, it is written Spectroscopic Techniques in Chemistry Part 2, and welcome to the lecture. So the first and foremost page that comes in deals with IR spectroscopy, and this IR spectroscopy is nothing but our topic for the day. Okay. Now what is IR spectroscopy? If the question comes to us, what we will be answering? See, infrared radiation refers broadly to the part of electromagnetic spectrum which is between visible and microwave. So infrared radiation actually starts from the microwave end and it ends at the visible end, right? After visible there is UV, there is separate end. So between microwave and visible spectroscopy we are having the IR range, and it consists of three parts basically: the far IR, mid IR and the near IR region, okay? Of greatest practical use of organic chemistry is the limited portion between 4000 to 400 centimeter inverse. Now, as you know that it is a huge range starting from near IR to far IR, right? But we chemists, we basically use the region between 4000 to 400 centimeter inverse, okay? Now, when IR radiation passes through a sample of organic compound, some frequencies are transmitted through the sample, which being absorbed. If we plot this absorbance or transmittance against frequency, then what will happen? We'll be getting an IR spectra, okay, or IR spectrum, right? Now in this particular lecture only we'll be seeing how an IR spectrum looks like, and how by using simply an IR spectra we can predict what type of functional group is present in a particular molecule, okay? So let us go into the details. Now first of all we need to see what is the principle of IR spectroscopy, and here we can see that when energy in the form of IR is applied, then what happens? The molecule will vibrate, right? Because this IR results from vibrational frequencies. So basically what will happen whenever IR radiation will be exposed to a sample, then what will happen? The natural frequency of vibration will take place, the absorption of IR takes place, and the peak is observed, right? Now molecules are excited to the higher energy level from the ground state when they absorb IR radiations, and when the compound is exposed to IR, it selectively absorbs radiation, resulting in vibration of the molecules. Actually this vibration basically, it is written that it results in the IR absorption spectra, that's okay, but what we can see from practical experience, that basically what happens, all molecules does not absorb the same wavelength of light, okay? What happens, whatever functional group is present in the molecule, depending on that only the absorption occurs. Now whenever some light will be absorbed, and we'll be say checking which one is getting absorbed, then from the data list we can easily find out that what type of functional group is present in this particular compound or the sample that is under investigation, okay? So molecules made up of atoms are linked by bonds. The movement of atoms and the chemical bonds like spring and ball, right? So basically, as this is vibration spectroscopy, there will be this sort of activities between the atoms and the molecules that are joined by the bond. Now, what are the activities? Activities is nothing but the stretch form, the compressed form, and the equilibrium form of the bond length, right? So basically, stretching and bending are the two types of movements that people can observe, due to which IR spectra comes into being, right? And this particular vibration is called natural vibration. Okay, what's next? So in this slide, we have come across the different important condition, that is conditions for the molecules to be IR active, right? Now this is a very important point, because all the molecules that are present that will not be IR active, there will be selective activeness under which the IR spectra will occur, or rather we can say that all molecules does not have the capability to form IR spectra, only selective molecules have the capability. So it is written, not all the bonds in a molecule are capable of absorbing IR energy. Only these bonds, only those bonds which have a dipole moment are capable of absorbing infrared energy. This symmetric bond, which are symmetrically distributed, will not absorb in the IR region. Now, this is very important. So when a molecule is having permanent dipole moment, or when a bond is having permanent dipole moment, then only that particular bond or that particular species will be IR active, otherwise not. So as you can see, there is a list of the molecules where the vibration frequencies are given, right, whether they are IR active or not. So for C single bond O, that is present in alcohol, ether, carboxylic acid, etc., the corresponding wave number will be 1300 to 1100. Yeah. So for this particular compound, this particular range is given. Okay. Next, for C double bond O ketone, for aldehyde ketone carboxylic acid ester, we are having 1750 to 1680. Okay. After that, for C double bond O again, but for amides we are having a separate thing. For NH stretching and NH bending, for amines and amides we have two different values. For stretching, the value is very high, 3500 to 3100. For bending, the value is quite comparatively less, it is 1640 to 1550. Now for alcohols it is 3650 to 3200. For amines it is 1350 to 1000, and for mercaptans it is 2550. Okay. Now what are the conditions? Let's check it out. The change in vibrational movements would produce a net dipole moment. Homonuclear atoms are IR inactive. Heteronuclear atoms should be IR active, because it is supposed that they are having net dipole moment. For example, this particular molecule is O2, where both are oxygen, so it is IR inactive, whereas this particular molecule, which is HCl, is definitely IR active, right? Now as you can see, it is C double bond O, so carbon dioxide different forms are given: asymmetric stretch, symmetric stretch, in plane bending, out of plane bending. So basically stretching and bending are the two different type of exercises by which we are going to find out whether a particular given material is IR active or not, right? And in that course we people have come across this particular stretching and bending. So stretching can be of two types. One is symmetric stretch, another is asymmetric stretch. Now in the symmetric stretch, you have seen that from the both sides stretching is being done, but in the asymmetric stretch you can see that different type of stretching is being done. Okay. Now in plane bending and out of plane bending. In plane bending means total thing will be down. Out of plane bending one will be up, two will be down. Okay. So this plus minus means plus will be up and minus part will be down. Okay. So that's how it is. So now what we are having? We are having the fingerprint region. Very, very important point here. So what is the fingerprint region basically? So in spectral region, this particular zone is very important for us, that is 1430 to 910, right? And this particular zone is called the fingerprint region. Okay. Why? Because the maximum bending and absorption bands and stretching vibration occurs in this particular zone. Since in a molecule bending is more general than stretching, the region of the spectrum is particularly rich in absorption bands. Which region? The fingerprint region we are talking about. Okay. The complex combination of bands as a whole is tightly typical for molecular structure. Hence, it is extremely useful in conclusively establishing the idea of two samples. But the fingerprint region will usually be having discernate uh, differences. Now, this is how the IR spectrum looks like from top to bottom, right? And you can see different type of groups has given peaks in different areas. So this is the IR spectra of one butanol, and we can see the broad peak is given around 3000 something by OH. I am talking about this particular peak. After that, we have got different peaks for single stretch, for OH stretch, for CH2 stretch, right? Now, fingerprint region, here it is written fingerprint region complex are difficult to interpret, and focus analysis on this region where the maximum stretching frequencies occur. That particular region is called the fingerprint region. Okay. Now, what we are having? We are having applications of IR spectroscopy. As usual, this is the last slide of this particular topic, and let us see what we are having in this particular slide. So, what we are having, the functional groups from the bond frequency present in an unknown compound can be identified by correlating the absorption frequency with the data. Okay, fine. So, what are the applications? Main application is by detection of functional group, right? That is the main application of IR spectra. Some other applications are to find out the purity of the sample, to study the chemical reaction, and to detect the presence of water in a given sample, right? These are some of the activities that we people can easily find out from the IR spectra. Okay? So how the determination of purity is obtained? So basically, if you know what the structure of a compound is and you take the IR spectra, so and if any impurity is present, so along with the peaks of that particular sample, there will be some additional peaks which will imply what is present inside the sample. Okay, so similarly, study of chemical reactions can also be determined from this particular thing, as well as the presence of water in sample can also be discussed from this particular thing. Okay, right. So this was all about the IR spectroscopy that we people are having. Now, in the last lecture, we have seen about UV visible spectroscopy, and in this lecture, we have seen about IR spectroscopy. Okay, so in the final lecture, there is the last lecture, we'll see about NMR spectroscopy, and our journey for chemistry BTech first year will end here, right? So let us hope let us wait for the last lecture. That is lecture number 35. Until then, you stay safe, study chemistry, right, and be happy. Okay, thank you so much. See you in the next lecture.